Hey guys, what's up? This is Gokul. Welcome back to another video. So today we're going to be talking about one of my favorite papers that's been released in the last year. It was actually released in October 5th, 2022. And look, the long and the short of it is this. This is the king of algorithms. I mean, for all other algorithms, it's time to pack up your bags and go home. I mean, this paper has these researchers at DeepMind have discovered the GOAT of all algorithms. I mean, it's not even funny. It's not even funny how impressive this research is. Nothing I've seen in the past year in medical AI or elsewhere. I mean, not even ChatGPT, or GPT-4 rather, and ChatGPT, not even those devices or those technologies impress me to the same extent as this paper. But this paper is titled Discovering Faster Matrix Multiplication Algorithms with Reinforcement Learning. And that is exactly what they do. So they train an algorithm to find better algorithms for matrix multiplication. And they do so using deep reinforcement learning. So why is this so impressive, right? The long and the short is this. Deep learning requires, to train deep learning models, you need to perform millions of matrix multiplication operations. I mean, that is the crux of the whole training process, just multiplying matrices together, okay? And so if you are able to find a faster way to do this matrix multiplication, you guarantee faster training. And if you can train your models faster, right, you can iterate faster, you can develop better models faster. So the idea here is this something like an incredible virtuous cycle. So you use this algorithm to find better matrix multiplication algorithms, which allows you to produce a better matrix multiplication finding algorithm in the first place, and so on and so forth. That is the crux of this paper, okay? And it's really an amazing advancement in my mind. And you have to give, this is beautiful work from the authors at DeepMind. So you have to give credit where credit is due. I mean, these guys they've solved chess, they've solved Go, they've solved protein folding, and now they're solving such a fundamental mathematical question, right? How do you perform better matrix multiplication operations? And by the way, this isn't just finding algorithms that are better that no one uses. No, mathematicians are actively using some of the results, right, that have come out of these papers to find even better algorithms. So it's this incredibly productive paper. But yeah, so shout out to the folks here at DeepMind, to all of the authors on this paper. I mean, this is unbelievable work, and I am so thankful that that there are people like this pushing forth the cutting edge. Okay, so with those remarks out of the way I see this video going, right, is I just really quickly want to just introduce the problem of matrix multiplication, as well as the way in which it's currently done, right, and some of the known algorithms. So we'll speak about the brute force and the Strassen algorithm, as well as the general notion of block decomposition. I'll also talk about some other algorithms which are kind of reminiscent of this algorithm, like the Kurzgesagt algorithm. And again, just to be clear, I'm not going to dive too much into the core algorithmic details here, largely because one, I'm not qualified to. Two, I don't understand the material with enough depth to really speak about it in an enlightening way, in any way. And three, I think you just need to spend a lot more time, than I've allocated for this video in order to do this task with any success. So I'm just going to kind of speak at a high level about the problem and the algorithms. I also want to briefly describe the paper and kind of the crux of the cleverness, right? Which is, it's one thing to say, we use deep learning to solve this matrix multiplication problem, right? Or the problem of finding algorithms to efficiently multiply matrices. It's another thing to actually implement something that does that, right? So it's how do you actually reduce the problem of finding algorithms, right? How do you reduce that to a problem that is capable of being solved by reinforcement learning and deep reinforcement learning? That is the crux of the cleverness. So I'll speak a little bit about this idea of reducing problems in CS and in algorithms. That's that has got to be one of the nicest takeaways, right? So I studied CS in undergrad, and one of my favorite professors, he's a complete beast. His name is Deep C. But one of the lessons, right, that I've taken away from his class, because he taught algorithms, was this notion of finding proper reductions, right? It's one thing to have an algorithm. It's another thing to know when to apply it, right? And oftentimes the art, right, is in actually seeing a problem, realizing, okay, actually this problem is an instance of this other problem, right? In other words, you can reduce problem A to problem B, And if you have an algorithm to solve problem B, now you can solve problem A. And that's like the real cleverness here, which is figuring out a way to reduce this problem of discovering faster matrix multiplication algorithms into like the relevant format needed for these reinforcement learning algorithms. And yeah, finally, I guess I just want to end with some closing remarks about like the general beauty of algorithmic reductions, right? Like, and how this is, I think, a broader life lesson, right? Like, it's oftentimes the difficulty in life isn't so much knowing what to do, right? But it's like knowing when to apply the knowledge you have to a given task, right? So it's often not so much a matter of lacking tools, but knowing how to apply the tools you have in clever ways. So I want to speak a little bit about that. But okay, yeah, but with that out of the way, let me just introduce the broad problem of matrix multiplication, right? So suppose you have some n by n matrix, right? And you're trying to multiply it with some other n by n matrix, okay? So for those who've taken linear algebra, you know the problem reduces, right, to like essentially you take this row here, you multiply it with this column, right? You take the same row, multiply it with the next column, and so on. And you do that for all of the rows here and for all of the columns here. So in this way, this naive algorithm where you just take the row, multiply by the column, and so on, takes roughly order n cubed time, right? So because they're going to be n, they're going to be n rows. So, or I should say, the length of one row is n here. There are going to be n columns, right? So that's already n squared, and then you do this n times. So that's where you get the n cubed. Now, in 1969, Strassen published, and he, by the way, shout out to this guy. He's a complete animal, dude. He's a complete beast. Okay, so this guy discovered a better way to multiply 2 by 2 matrices, right? So, per what we've just said, a 2 by 2 matrix should take 8, order 8 operations, but Strassen devises a way to do it in 7. And, essentially the idea here is like, not only can you do this with 2 by 2 matrices, right? But the idea is like, you can actually reduce any, any power of 2 matrix. You can reduce that to a problem of essentially solving these smaller subproblems, right? So you can decompose some 2 to the k matrix, right? You can reduce that to a problem of actually just 2 by 2 matrix multiplication, right? By taking each of the 2 by k minus 1 subblocks in each of the matrices, right? And just calling it like A, B, C, D, and then E, F, G, H here, right? And each of these are 2 to the k minus 1 size matrices, right? I guess dimension matrices, and so on. So you can apply this Strassen algorithm recursively, and inductively you can show that this algorithm gives you something like n to the log base 2 of 7 complexity. So if you do the math, right, that's just under 3. It's like 2.8. But as n becomes large, this is a tremendous improvement. So this algorithm, by the way, this Strassen algorithm is also reminiscent of another algorithm that Deep C taught us in our algorithms class, which is, I think it's for polynomial multiplication, where you do like a similar thing, right? So on screen, right, like you should have seen basically how the Strassen algorithm works, like how you're cleverly adding together these numbers to give you all of the portions of the subsequent 2 by 2 matrix. And you can do a similar thing for polynomial multiplication with the Karatsuba algorithm. It's the same divide and conquer idea, and you can do so recursively. So now let's turn to the paper, right? So we'll just read the abstract, right? Because I can't understand the methods, and if you understand the methods and you're watching this video, it's time to leave. You're wasting your time. But so in the abstract, right, they write basically improving the efficiency of algorithms has tremendous impact. And as I hope to have shown, right, like it really does. And matrix multiplications is such a fundamental task, right, that occurs everywhere. So the automatic discovery of algorithms using machine learning offers the prospect of reaching beyond human intuition and outperforming the current best human-designed algorithms. However, automating the algorithm discovery process is intricate, as the space of possible algorithms is enormous. That's right. First of all, it's difficult to even wrap your head around what that space is, right? I'm not even sure what the space of all possible algorithms for, say, 3 by 3 matrix multiplication is. I don't even know how you bound that, but they're able to bound it somehow, and they're saying it's huge. Here we report a deep reinforcement learning approach based on AlphaZero for discovering efficient and provably correct algorithms for the multiplication of arbitrary matrices. AlphaZero, dude, this algorithm is carrying DeepMind. They're using it to solve chess. They're using it to solve Go, right? They beat that Go grandmaster, and now he's unemployed, I heard. I actually don't know that, but he might be. And then they're using it to solve protein folding. It's game over for literally everyone. So our agent alpha tensor is trained to play a single player game where the objective is finding tensor decompositions with a finite factor space. Imagine having a kid and just training him to find tensor decompositions so you can find a better matrix multiplication algorithm. I mean, that's insane. Alpha tensor discovered algorithms that outperform the state-of-the-art for many matrix sizes, particularly in the case of 4x4 matrices, right, where alpha tensor algorithm improves on Strawson's two-level algorithm for the first time, to our knowledge, since its discovery 50 years ago. So again, I think the two-level algorithm is just decomposing this, right, 4x4 as you recursively solve the 2x2 subproblems, and it finds a better way of multiplying 4x4 outright. We further showcase the flexibility of alpha tensor through different use cases, algorithms with state-of-the-art complexity for structured matrix multiplication, and improved practical efficiency by optimizing matrix multiplication for runtime on specific hardware. Our results highlight alpha tensor's ability to accelerate the process of algorithm discovery on a range of problems and to optimize for different criteria. Unbelievable. I mean, completely unbelievable. This is easily one of the coolest papers I have ever seen in my life. I mean, you're using an algorithm to find better algorithms that you can use to make the algorithm better. Unbelievable. Actually unbelievable. And with you put this guy in the same room with ChatGPT 4. I mean, what are they not going to be able to do together, right? You have one kid cooking up the best algorithms, the other giving you all sorts of crazy commands, coding. Yeah, I mean, it's unbelievable. So anyways, yeah, I mean, let's not really get into the meat of the paper. Unfortunately, this is so far outside of my expertise, I'm not going to be able to say anything insightful, so I'm not even going to try. But again, the real cleverness here, again, we can just briefly look, right? But they decompose, like they figure out a way to reduce the problem of finding these new algorithms to like a problem that is interpretable, right? Or a problem that can otherwise be cast in language that the reinforcement learning algorithm can understand. And so that's really the other clever part of this paper, right? So how do you reduce the problem of discovering algorithms to a problem that you can solve with existing tools? Okay. And so that sort of brings me right to the next portion of this video, which is, this larger insight, how can you reduce problems to instances of other problems and use algorithms that we know to solve other problems, right? In these cases. And that is, I think, I honestly think, like, for me, particularly given the nature of my research, right, where what I'm doing a lot of times is applying techniques that have been devised elsewhere, to questions of biology. A lot of the times, the applications that I have done have been rather straightforward. Okay, here's this better, image classification, object detection, instance segmentation, text embedding model, right? And it's obvious to see how improvements there, right, can improve the performance, right, on tasks. That's pretty low hanging fruit, I'd say. The more clever types of techniques are like, okay, well, we have these. I covered a paper recently, right, about titled AI Pathologists, where I was looking at recent research out of the Mahmood lab, and there, they were co-embedding. They're training a model to basically co-embed language and text. Sorry, language and images rather. That's more clever, right? That's like using a technique that is like less obvious that this is going to be useful for image classification. But if you're clever enough, you can find a really nice way to actually reduce the problem of classification as one of finding, the index in this similarity score vector, right, that is highest. Okay, that's like sort of like your mid-order complexity, right? Impressive. And then there's the stuff these guys are doing, right? So finding. I'm just dumbfounded. It's like playing God. I don't know how else to describe it. I mean, it feels like you are just fundamentally, we're getting closer to like the nature of like the fundamental fabric, right, of the universe when we make discoveries of this kind. So, yeah, I mean, and in like algorithms class, right? Like for me, it was always difficult. Like, how do you reduce this problem of like scheduling? Right? How do you reduce this problem of scheduling to like a max flow min cut? How do you apply the Ford-Fulkerson algorithm to this problem? How do you reduce this graph problem to a problem of simply finding like the min cut, right? Or like how do you reduce this scheduling problem? A different scheduling problem is like finding a specific topological ordering, right, among nodes in a graph, right? I mean, so it's an art, and they have done the art beautifully here. And that's really all I want to leave you guys with here. Unbelievable research out of DeepMind. I mean, at this rate, there's really going to be nothing left for us to do. Right? In a couple of decades, we're just going to sit around, on a beach, hopefully somewhere in Bali, doing cool stuff while the robots figure out, how the universe works. But until then, I'm going to be ecstatic to continue following the development out of these labs. And this is just tremendous work by these researchers. So anyways, guys, yeah, that's really all that I wanted to talk about in this video. If you found this video entertaining, educational, interesting, please leave comments, please subscribe. And, just feel free to share your thoughts, right, if there are things you'd like to see. Anyways, yeah, that's it for me. Thanks, guys. Take care.